Welcome to another RDWorks Learning Lab. Today it might get a bit technical because we're going to get involved with a subject that I wouldn't say I've failed, but I certainly haven't succeeded with grayscale engraving on this Tangerine Tiger, which is an RF machine. Now, an RF machine is very similar to a machine that many other people use, which are the diode lasers, which operate by PWM as well. This is a PWM controlled machine. And there are all sorts of strange properties associated with PWM and the way in which you might want to use it for grayscale engraving. Now, this session is going to be broken down into two parts. First of all, let's understand what the PWM system is and how it is applied to grayscale engraving. And secondly, and the most important thing is, how do we get grayscale on material? Because with the work that I've been doing recently with lenses and laser beams, this machine is never designed for engraving. It might be an engraving machine because it certainly doesn't cut very well, but it also has a tendency to cut when it engraves, which is not what you want. We're trying to scorch the surface of material and produce different colours on organic materials. I mean, you can't do this sort of thing on slate, acrylic or other mineral materials because it doesn't work. The only materials that you've got are things like leather, card and wood, and I don't include MDF in wood because MDF is a strange hybrid material which is a mixture of plastic and wood, and it doesn't have the colour range that you can get from normal organic materials. So with normal organic materials you can scorch from nothing to nearly black, very, very dark brown in fact, if you're lucky. And that's the thing, if you're lucky, you need to understand what you're doing to get the colours, because trust me, it's not easy. Understanding the machine is one thing, understanding how to get the colours onto the material is different. The guys with diode lasers have a much easier time because their beam is blunt. They may well have a sharp focus point on the material, but it's very low power and you can scorch very easily with a diode laser. It's almost impossible to scorch with a machine like this. It cuts. No matter what lens you choose or what power you use, it will cut. We're going to investigate first of all the PWM system on here. Now, I've already discovered the secret of how to get dithered images off this machine, and they are coming out fast and amazing. Something again that I'd failed at in the past, but once I understand what the technique was, then all of a sudden lots of other things fell into place, and I'm going to try and use that same technique for grayscale engraving because I'm sure that it will succeed where my previous attempts in the past have been close to abysmal. I'm going to be using RDWorks for this session because RDWorks has got a feature in it that doesn't really appear and is not as straightforward in Lightblade at the moment. Now here's a special grayscale file that I've created. As you can see, it runs from black to white, black to white. It's a sequence of two lines. And here we've got 50, 100, 150, 200 and 250 grayscale. So black is 0, that's 250, and this is 255 just here. And then it goes back to 0 again and out to 255 here. So we're going to use this to start with to explain roughly what's going on. Let's look at the parameters. I'm going to run this at 400 millimeters a second. Now 400 millimeters a second, I'm going to be using or trying to use a 0.1 dot. That's the nominal resolution of this pattern here. It's 254 ppi. Okay, so as you can see here, I've got a 0.1 pixel spacing set up, not because of this, but because of these. All right, this is only a single line, 1 pixel wide, which is purposely what I want to demonstrate and show to you some of the important features about the way that grayscale works. 400 millimeters a second, 0.1 pixels means that I'm going to have 10 pixels per millimeter. And if I'm going to run at 400 millimeters a second, it means I'm going to be putting down 4,000 pixels per second. And so therefore what I'm going to do, I'm going to go into this advanced section here, put my tick on here, and I'm going to run this at 4 kilohertz. That's the PWM frequency, 4,000 pulses per second, to match the 4,000 pixels per second that I want to put down. Now that's the most important part of this session, matching pixel speed to frequency. And here we've got 30% power. Okay, now 30% maximum power, and you'll notice that the minimum power is greyed out. Well, that's because I haven't actually selected Grayscale Engraving at the moment. So let's just have a look at something that's interesting. Here we see the red signal, which basically says, yeah, I want to run this program. So it switches on the program here, and what we're seeing is the pixels. All right, the pixels match the frequency. So you won't see anything different here. What you'll see is this piece here is 30% and this piece here is 70%. 30% on, 70% off. 30% on, 70% off. And look, they're all exactly the same. Okay, so every pixel is going to be the same color because it's got the same amount of exposure time on every one of the pixels. Now that's not what we want. So what we have to do is go back to here. And this time, look, we've got 30 and 30 greyed out. This is not Grayscale Engraving. To get Grayscale Engraving, what we have to do, we have to select this little switch here called Output Direct. And what that does, well, I'll show you. Let me first of all change this to 50%. And I'll change this one to 0. So here we've got Grayscale Engraving. If we look carefully, you'll see that here we've got 50% on, 50% off. But here we've got maybe 30% on, 70% off. And as we get towards the end of the pattern here, look, we've got maybe 1% on and 99% off. We're using the 0 to 255 grayscale pattern that's in the image to decide on the duty cycle for each cycle. So here we've got a smaller amount on than we have off. So this decides the colour. So here we've got white, where we've got no engraving at all going on, and at the other end of the scale we've got 50% on, 50% off. Why 50% on, 50% off? That's what I chose here. So I can never have more than 50% power, 50% exposure time per cycle, because that's what I've defined here. Anything between 0 and 50%, there are 256 divisions in between those two numbers, regardless of what those two numbers are. They could be 1 and 2%. There will still be 256 divisions between 1 and 2%. That's the way that this grayscale system works. One of the interesting things is what happens if you mismatch the frequency, and I'll explain all this a little bit more detail when we go back into the office, but it's essential for you to see this bit to start with. We're going to leave the speed at 400, we're going to leave our 0 to 50%, and this time we're going to change the PWM frequency to, let's go down to 2K, 2000. Doesn't appear to be doing anything different. So we're going to change that now to 1 kilohertz. So that's a quarter of the frequency that we were using previously. This is new territory for me because I don't know how this machine is going to react to this set of circumstances. Yeah, it's doing what I suspected it would do. It's missing a lot of information. Okay, let's see if we can put a bit more sense into what we've just seen in the workshop. Here's my pixels, and they're 0.1 square. And this is how they were in my pattern. They were running against each other. Now, as I said to you, 10 pixels equals 1 millimetre. And if I want to run at a speed of 400 millimetres a second, I'm going to finish up with 4,000 pixels per second. This signal here is the PWM signal. Look, there's one cycle up to there, up, 50% on, 50% off. and then it goes back 50% on, 50% off. And this is 4,000 cycles a second, 4 kilohertz, which is what we set up to start with. And we saw that we had a nice pattern that looked just like this. This signal, this PWM signal, is not necessarily linked directly to these pixels. Like I've shown here, look, it could be starting 50% across a pixel. But regardless of where it starts in a pixel, it's still a pixel wide. So therefore, there will be 50%, which I've got shown here, 50% on, 50% off. There will be 50% exposure time for that pixel. Regardless of whether it's 25% at this end plus 25% at that end and nothing in the middle, there's still 50% exposure time. So it makes no difference that the PWM is not synchronized to the pixels. If I set the max power to 50%, what I'm really doing is I'm setting this ratio here in a cycle, 50% on, 50% off. So I'm setting the on time when I say 50% max. Nothing happens about Grayscale until you put that direct output switch on. And then something interesting happens. Grayscale has got a scale which runs black equals 0 and white equals 255. That's 256 steps or divisions. And so this 50% on that I've got shown here is divided into 256 discrete increments. And here we are, look. We've got something which is, say, mid-grey. So we might have 30% on, 70% off. Then the next one is probably nearly white. So look, we've got nothing, hardly anything on, and a lot of off. And in this one, we've got 50% on, 50% off. So each one of these pixels assumes a different duty cycle depending on the colour of the pixel. Hence we get this strange looking pattern. Now you've seen this effect on my Grayscale line. And then as I move along here, we're still using 50% because we're still using the maximum that I set, and the amount that it's on per cycle is dependent upon the grayscale colour of each one of these pixels. It's an amazing bit of software to be able to do this. The point that I made originally is it's very important to make sure that your speed times your resolution equals the PWM frequency. Otherwise, you will start missing information. We've got one cycle, one pulse. Here we've still got one pixel, one cycle. If I decide to change the frequency of my PWM to say 2 kilohertz instead of 4 kilohertz, look, it's now spread out more. So what's going to happen now? This is still going to happen, right? But look, it can only happen on the plus side of the pulse. So this is the plus side on, and it can be varied by whatever the colour of that pixel is. But now the PWM is switched off, so it can't actually see that pixel at all. And then it comes back on and it sees the colour of this pixel, off, on, off, on, off. So we're missing 50% of the information in the picture. It's not being printed. And the same thing happens when we get to here. If we shift this down to 1K, we're now going to print 2 pixels and miss 2, print 2 and miss 2. But actually, that's not true. So this is what I had to check with my oscilloscope when I first got out into the workshop, because I didn't know how 2 pixels during the on cycle would be treated. Would they be treated as 2 pulses here? I couldn't see how that was physically possible, because it looks as though either the first or the second pulse is the thing that determines the width of this. The colour of the pixel is getting less because we're producing less and less exposure. The width of that first pixel could be that, or it could be that. I don't think it's that. I think it's this one. Okay, so it'll be, say, a mid-grey, and it will stay mid-grey even though that one is nearly white. That one won't be taken any notice of, that one won't be taken any notice of, and that one will be the colour that it's set to. So we're actually distorting the image that we're putting in our grayscale image. It's no longer anywhere near what we started with. So this is the mechanics of grayscale and how it works. It's all to do with exposure time causing damage to the material. And we can only get the correct exposure time if we use 1 pixel, 1 cycle. Okay, let's move on to part 2, which is all about how we're going to mark material. I'm going to quickly grab a couple of pictures from a previous video that I did, which I advise you to go and look at because I'm not going to go through all the detail that's in that video here. The first thing is every, and I mean every, lens which is designed with this thing here, which is a spherical geometry, has got something called spherical aberration. It's a naughty fault that we can't get rid of. Well, not entirely true. You can try and get rid of most of this strange focal situation here by putting a further curvature in the bottom of the lens. And that reduces this aberration here by about 95%. It doesn't get rid of it completely, but it gets rid of most of it. So what is aberration? Well, aberration means that you don't have a single focal point, because the rays that come in from the outside of the lens are focusing at a different point from those rays that are coming down the central part of the lens, which is down here. So we get quite a big change in the focal point of various rays as they pass through the lens. For optical engineers, this is a bit of a nuisance because it means you get a fuzzy focus and you don't get very good quality pictures out of the end if you're trying to use it as a telescope or a camera or something like that. And this is what happens when we turn the lens over. We flip it the wrong way. We only get 1 refraction, not 2. That 1 refraction comes off this curvature here, which again is a spherical geometry, and it's got the same sort of problems but 100 times worse, as you can see. Look at this way, look at the way in which the rays are being refracted all over the place. But the thing that they don't show you on these diagrams is what's tending to happen right here close to the central axis. Now, I've tried to explain this in my previous video, that I've used coloured rays to show the way in which these rays converge on the, let's call it the fuzzy focus down here. Okay, now we don't have uniform rays across here as light going into a telescope or a camera. These are special rays that we've got where the intensity of the rays changes as we go across the beam. And we've got very high intensity rays right at the centre, and right at the centre, which is very close to the axis of the lens. This aberration is the key reason, after 3 years, that I've found out we can cut with a lens. Every lens has got a weakness, spherical aberration. Some are worse than others, as I demonstrated in the 2 previous diagrams. What we're interested in for cutting or engraving is what's happening here. Subsequent to my doing all this work, I discovered an amazing piece of software which simulates spherical aberration. And I can set this up for various lenses and I can see what's happening just here. So we can zoom in on what's happening just there. And I think you can see, look, we've got exactly this effect that I described to you. We've got rays that are coming from the outside that are focusing at different points to the rays that are coming down the centre. These here are the most powerful rays because they're coming through the central axis of the lens, and they're also in the central part of the beam. And they're being focused not at a point, but at a range of focal points down here, away from this nominal circle of least confusion, as the optical engineers want to call it. Well, as a laser user, it's not a lot of use to us because we're not trying to use these lenses in telescopes or cameras. We're trying to damage material with them. And it is this very high intensity spike of energy which is passing through the centre here, which causes us a problem when we come to engrave. So let's just backtrack a second with my coloured rays and say this is the point where you are going to do your engraving. Well, at this point, these red rays haven't even focused yet. They're going to focus down here. Now, the intensity profile across here is not going to be Gaussian, because look, all these rays are coming in from all directions and flying off in all directions. So what we had to start with is not going to be what we have here at the point where we're going to do our work. What we're going to have here is an intensity profile which will still be very high at this central point here, but it'll drop away lower at the edge. Okay, but most of the stuff that we get here is going to be the red rays, which are the very high intensity central part of the beam. Now, you would normally consider that a very short focus lens is the perfect lens for engraving. That's what we're told. You know, 1.5 inch lens, perfect. And here it is, a 38.1 meniscus lens, which focuses to a point. Remember, if we put a meniscus shape underneath, it helps to improve the focal point. It takes away the aberration by 95%. Well, here we've got a couple of tests. Now, these tests are done the same way up, and what you've got here is 2 tests, and I've pushed them back to back so that you can compare the difference. Now, this is 1.5 inch focal length lens after 2 milliseconds. You might just be able to see a little teeny weeny mark in there. 4 milliseconds, 6, 8, 10, 12. Hang on. This is the lens used the right way round. What happens if I turn it the wrong way round? The naughty boy using things as they shouldn't be used. Look, it's already about 5 times more efficient at cutting than the right way round. Look how quickly this thin beam is penetrating in relation to the right way round. And this has got a phenomenal amount of aberration in it. This one has got not much aberration because it's a meniscus lens. What do you think now? Well, what it amounts to is, if you use a meniscus lens the right way round, it's not going to do much damage. If you use it the wrong way round, which you might want to do for cutting, it's going to do substantially more damage cutting for you. Right, so the last thing we want is a meniscus lens used the wrong way round. So here's a standard 38.1 plano convex. Look, it's already less efficient at engraving and more efficient at cutting than the meniscus lens. So you certainly don't want to use a plano convex lens for engraving. If you want to use something, use a meniscus lens. So I'm not going to go too much further into this, other than to say that there's a hell of a lot of detail in here, a lot of work that I've put in over 3 years to discover the thing that optical engineers don't want in a lens is the one thing that we do want. And what it turns out is exactly the same as all the parameters for cutting and engraving. They're opposite each other. And here we are again. Use the lens the right way round and it's better for engraving. Use it the wrong way round and it's better for cutting. I will direct you to a website called laseruser.com. And there is a series of videos on there which I produced, which basically is like the A to Z of laser technology. And one of the sessions, session 18, deals with the difficulty of producing a black mark on the surface of material. So that lovely thin black line there against the white background of the poplar plywood. Now when we catch that in the light, I think you can clearly see there is no black in there at all. It's a lovely clean vaporized surface in there. So where did the colour come from? Well, the colour came from occlusion of light. There is no light getting into that groove there. So consequently, it looks black or brown. This was a cut that was done right the way through. We've only used the high intensity central part of the beam to cut into the surface. And it's cut into the surface, leaving no brown at all. There's no scorching on that at all. So that's the problem that we're going to have in trying to laser engrave grayscale. How do we get colours? Because this is not a real colour, this is a false colour. This is a real colour. And that's achieved with low, very, very low intensity. So how can we make our laser beam less intense. Well, unfortunately, with an RF machine, we can't. We're always throwing 100% power at the material. We might be not throwing 100% of power all the time. It's the same shape beam, whether it's running at 1% or 100%. The only difference is at 100%, this shape will be wider. We've got the same conical beam in every situation between 0 and 100% duty cycle. So one of the ways of controlling our beam width is by reducing the duty cycle. And we will come across that, and I'll demonstrate that to you very clearly in a minute. Now here's that material that I described to you earlier that I didn't think was very good for engraving, and it's MDF. It's got lots of other uses, but look, here's the raw surface MDF, and here is some engraved part of it. Okay, while I'm setting up something else. You can see here, look, we've got some little teeny weeny pits which look dark, but generally here what we've got is a slightly brown because of the way in which the laser beam has interacted with the plastic binder in the material. That's not brown because of burnt wood, so you need to be very careful with your choice of materials when you attempt grayscale engraving. You want something with a huge contrast and something that will scorch with a wide range of colour. MDF is not that material. You can go to laseruser.com and look at session 18 to see that video and understand more about the difficulty of actually achieving a scorched surface rather than a cut surface. Okay, now what you see on the screen there is a piece of white soft beer mat card. It's basically wood pulp, so I can't get any closer to grainless wood than this. And as you can see, it's got a very wide colour range from black through dark brown, mid-brown, out to background colour which is white. I just put that up there for demonstration just to show you the range of colour that is possible with this particular material. Now because it's only 20% power, it's not particularly deep, but I think you can clearly see that it has got depth to it. Look, each one of these is a little pulse. So with 20% exposure, you can see that it is tending to drop off at the end here where we've got 0. Okay, it's not as clear on this one that we're getting a change of beam size because of change of power, because we're starting off with such a small percentage anyway. So let's change the percentage duty cycle now to 50%. And aha, we're getting some colour. Well, I wonder whether we are getting colour really. Because if I move the light around, what we're seeing are shadows. There's just a small amount of scorching there, but if you look carefully you'll see that most of them are little coloured pits. And as the pits get shallower and shallower, the colour disappears. I mean, these are 100%. Okay, and this is probably quite a good indication that we've got the right size dot here, because look, these dots are just about touching each other, which means those are about 0.1 dots, which is perfect for what we want. So this is 80% duty cycle, and we should have some really black marks now. Not really very good really, are they? We've got a little bit of colour here, but that's not colour, that's depth. Like these are depth, because if I catch the light in those right, I'm sure I will be able to remove the colour. Let's just see if I can do that. So it's all, most of it's shadow. In fact, if I turn the top light on, maybe. So that's through the lens light, which is directly onto the job, and you can see that there's virtually nothing there in the way of a scorch mark. It is just nice, clean, almost vaporization. So that was from 20% all the way up to 80%, and we haven't changed much at all. So how can we get colour? Because all we're doing is we're basically doing what I predicted we would do, which is cut. We've got a very sharp vaporizing tip to our beam. The lens that I've got in here is a very sharp focusing compound lens. It's designed to focus light to a specific point, and it does a great job. Now I've done the same test on acrylic with a bigger dot. So here we are, full black at 99%, and then we travel down, and as you can see the beam is getting thinner and thinner and thinner, and it's almost disappeared. There's not enough intensity in the light to actually damage the acrylic, and this is one of the reasons why the guys with the diode laser have a much bigger advantage. The diode laser operates at a much different wavelength than our 10.6 microns, and down at 450 nanometers the damage that you can do to wood is a lot less. Wood is a lot more resistant to the approaches of 450 nanometers. It doesn't give in as easily, so it doesn't damage as quickly. So consequently, it's very easy to scorch wood with a diode laser. We're up at the other end of the spectrum, and it's very difficult for us. And bear in mind, I've only got 30 watts here, so 100% is 30 watts. So let's see if we can look at a side view of that. So look, it starts off black, fully deep, and then it gets shallower and shallower and shallower, and then we're back to 100% again in the middle of the screen, and then it starts dropping off again for our second pattern. Whereas in fact we're trying to work now to get the right size beam. We're trying to work at 20%. I've had to adopt a slightly different strategy now to get some colour into the engraving. So with 20%, I've now got a line thickness which is about 0.2, which is not what I want, but I've got some colour. And the reason why I've got colour is because I prepared this piece of card beforehand with borax. Now borax, which is what we're seeing on there, boron, is a shiny metalloid material, and that's the colour that we're seeing developed on there. There is no colour range to borax. What we have got is something very interesting on there. We go from thick, as you can see quite well, we go from thick to thin. I know it disappears to nothing there, but there is definitely a width as the percentage changes. Okay, well, what we've done there, I've readjusted the focus and changed the power to 30%. We've got a line which is now less than 0.1, so that's 30% maximum, and then 250 shades of grey later. We've still got just a hint here of colour, but of course these are all basically the same colour. They're not really changing. It's all black because that's what borax is. It's black. The end result is boron. So this leads me to thinking we shan't be able to do grayscale engraving in the normal sense of the word, because as you can see, any grayscale engraving is going to give a different depth and a different size of dot. Leads me to something else, another idea to help me out with decent, maybe fingers crossed, grayscale engraving. Now you may or may not have come across this before, but that is a famous engraving. Look, it was done in 1649, but look at it carefully, and what you see is, look, all this texture around here. There's single lines of various thicknesses. Hang about. Single lines of various thicknesses. Isn't that what we've just seen under the microscope? Look at this. It's all one single spiral engraving, the whole thing. It's absolutely phenomenal. This is an inspiration I may try to follow. Not spiral, but straight line engraving with different gaps between the lines, just like this. I wonder whether that's going to work. Well, I have to say, as a first attempt, this is looking pretty interesting. I'm finishing up running this at 40% duty cycle.
Okay, so there's the end result. Now, I have to say, I'm not into perfecting this technique. It's a demonstration of the technique. All I can say is it turned out substantially better than I thought it ever could do. My previous attempts at grayscale engraving have been, to say the least, fuzzy. This is not fuzzy. This has got some pretty good detail in it. And it tends to verify the technique that I'm using. What we're going to do now is I'm going to get a piece of this card which has not been treated with borax, and we'll run the same program again. The replication is very good, the colour is not, and that's the problem that we're going to have with normal organic material. We're basically cutting into the surface, we're not making it brown. Now I've turned the machine off so we can get some peace and quiet to just step back for a second and see what we've discovered here. This, I suppose, would be classed as normal grayscale engraving. Who knows what the pulse width would be, and who knows what the resolution would be. I don't think people have normally considered that there's a relationship between the two, but I definitely know that there is, because look, we've used 1 pixel here equals 1 PWM pulse, and we get a pretty good replication of this, but we're not able to get any colour contrast in here because we haven't got the scorch power in the beam itself. We've got cutting power in here, which is actually producing lots of very small cuts. Let's check the lens out. We'll just put a pulse down on here. Look, it's got a great ability to scorch with a lovely black mark. Why aren't we getting the colour into this image? Well, obviously it's because, as I said before, we're putting very thin lines in here which are too deep. They are not scorching. They're cutting lines, not scorching lines. This has been treated with borax, which has removed the colour range from this card. But hey, look what we've got. We've got colour and we've got a picture. But this is not what you would normally class as grayscale engraving. Because I've turned this from a multicolour capable piece of material into a single colour binary piece of material. That's mad. What that really means is I should be able to do grayscale engraving on this stuff, which is another binary material. It only has 1 colour that it produces. You can't do grayscale engraving on slate because it is exactly what it says, a binary material. It does not have any colour range. But hey, we've been able to get colour range into a binary material without going to dithering, which is the only way that you can normally get a photograph onto a surface like this, dithering process. So we should be able to achieve this on this. With such a short focus length lens, I think I've got a little bit of a problem here because this is slate and it's not very uniform, and although I've tried to set this up reasonably square, it looks as though we've got some focus drop off down this side here. But hey, regardless of that, the results that are coming out are pretty phenomenal considering this is not supposed to be a grayscale engraving material. Well, I think you can see that from the parts that were in focus came out well, but I think we've dropped off something here. It could well be the focus, or it could well be the actual beam itself. I'll go and just check the beam and I'll show you what I mean in a minute, how important the beam shape is to the quality of the product. Now, we're just going to do a mode burn at the corners of the picture so that we can see what the beam shape was like before it went into the lens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, as we can see, all of those mode burns are pretty crap, to be honest. They're abysmal. But having said that, that's what they claim is the right sort of beam shape for engraving. In other words, you've got a very poor central intensity, which gives us an ability to scorch rather than to burn. Well, we've been using that and it hasn't given us any scorching ability at all. You wouldn't be able to cut with that beam. It's absolutely useless. It's the shape of the material, the fact that it's dropped off on the edge, that's caused the problem, because it's not the beam quality itself. The beam is fairly consistent on all four corners of the job. What have we learnt today? Well, it's something quite amazing really, because it turns out that grayscale engraving on an RF machine is pretty rubbish. Yet, here we are doing grayscale engraving on an RF machine with a non-colour range material. This is a binary material. I know it's card, but I've converted it into a binary material with painting it with borax. Technically the pixels should all be the same size and the dot should all be the same size, and the only thing that should change would be the colour or intensity or exposure time of the dot. But because the dots don't remain the same on an RF machine, as you decrease the power we get a decrease in the dot size. We're getting some strange sort of hybrid effect, which allows us to do grayscale engraving by virtue of varying dot size on binary materials, as we've proved. Now, this is not what happens on a glass tube machine, because we've got a different sort of control over the beam. We can make the beam softer. We can make it into more of a scorching tool rather than a cutting tool. What we can do, I hope, is show you next time how to exploit the speed benefits of this machine on a glass tube machine, because I believe we can sort of produce a hybrid effect of this and what we see on a glass tube machine to produce some pretty interesting and rapid results. I might be able to even photo engrave at 1,000 millimeters a second using grayscale and a glass tube machine. There's an interesting thought. We'll see how far we can get with that in the next session.